Okay, so in the last video of this topic, we talked about simple interest. And we essentially defined this as some interest calculated on an original amount of money on a loan or any investment. So I'm actually going to write down this little definition that we came up with because in financial maths, our definitions are important. They allow us to distinguish between these different types of calculations we work through. So for simple interest, this is essentially calculated on the principal. We introduced that word principal, which essentially just meant the original amount. Now, let's look at how compound interest differs from this. Now, compound interest, like simple interest, is calculated on the principal amount, but in addition to that, it is also calculated on the accumulated interest from previous periods. So let me write that down, and we're going to get a bit more into this and derive an actual formula for compound interest. So compound interest, let's actually write it down here. So like simple interest, it is calculated on the principal. So I'm just going to do these little like quotation marks just to say that this is pretty much the same as simple interest. But it's calculated, the interest is calculated on that as well as the accumulated interest. Accumulated, we just mean the interest that's been gained. Accumulated interest of previous years. Okay. Here are our two definitions. So let's work through an actual example. I won't do an example on simple interest because I have another video for that. But let's actually look at a concrete example. And we're going to use this example to hopefully be able to derive a general formula. So obviously where formulas are useful, they give us some kind of general method where we can just input in any numbers. We don't have to do all the grunt work that I'm going to be doing now. So here we have an example that someone borrows $5,000 from a bank at a rate of 9.2% per annum. And remember, per annum just meant per year. And this is 9.2% per annum compound interest. So this is different to the simple interest we dealt with before. And we want to calculate the amount. So we want to find the amount owed after, let's say, 9 years. So here are our important bits of information. We had the amount he borrowed, the compound interest rate per annum or per year, and the amount of years. Well, the amount he owes after 9 years. So let's look at what compound interest, let's look at how this works. So this person's starting amount or principal. And you'll see that these same kind of letters we use from simple interest pop up again. We have our P, we have our principal, we have our rate R, and we have our number of years N. So this compound interest has the same elements as simple interest did, but the way it works is a little bit different. Now let's go back to this. Our starting amount was 5,000. Now let's find the amount this person owes after a year. So after 1 year, well, we can say that if $5,000 and interest here was calculated at 9.2% per annum. So after 1 year, he's pretty much paying this in addition to 9.2% of this sum, right? So this is getting added to 9.2% of 5,000. So we still have our starting amount, and this is important to note. We have our starting amount plus our rate, and our rate as a percentage of this amount. So calculating that, we are going to get, well, we're going to get 5,000. And I'm going to write this in a different way, but it'll give you an idea of how this formula may start to look. So this is getting multiplied by, well, 1, because we have one lot of our starting amount, in addition to our rate. In addition to our rate here. And I'm going to write this as I can either write it as a fraction or a decimal. Now we've done these conversions in the past in my videos, so feel free to look at some of those, but this is a rate of 0.092. This is just that as a decimal. And that will get multiplied by our principal here. So essentially, I've just rewritten this just in a nicer, more compact way. And everything I've written here conveys this information because when I take this, I have my initial amount plus a percentage of my initial amount. So we can add what's in this bracket and we can write this as 5,000 times 1.092. So this is the rate that is applied to this. And this, because compound interest deals with the amount of money owed. So when we borrow money, for example, we're calculating at the end of each year and eventually finding, in this example, 9 years, we're going to find just the total amount of money owed with the interest included. Now, if we put this into our calculators, we should get about $5,460. Now, this is where compound interest is different because remember we said that compound interest is the interest on top of interest, pretty much. We take into account the principal amount as well as the accumulated interest from the previous years. So it's interest on interest, essentially. So if I were to find after 2 years, Well, I'm taking into account this thing because this number here, $5,460, was our principal as well as the as well as the interest applied. So if I wanted to find this, well, I would say that that is the money I owe from the previous year. That becomes our new sort of input, like this one here. So that will become 5,460 in addition to, well, itself plus our rate. This number becomes our this is our interest on the interest. And here I'm going to do 3 of these and we're going to see if we can find some sort of pattern that's happened. So I'm going to multiply this by my original, the money that's in at this point, as well as the rate increase. And I'll get 5,962 and 32 cents. Okay. Let's do this one more time, and then we're gonna find a pattern here. Because financial maths and later maths in terms of finance, it's all about these types of patterns. Now, after 3 years, I'm gonna have my amount owed. This is my total accumulated amount, including the principal, with my rate increase. And actually, sorry, let me rewrite this. I'll just skip that in between steps so you guys, because hopefully you've got the idea that these things are just going to sum to 1.092. And here we will get $6,510.85 roughly, rounded to 2 decimal places. So let's pause for a minute here. And I'm going to zoom out and we're going to look at what happened in each of these time periods. And I'm actually going to draw a little table here. And we're going to just look at kind of what happened each time. Now, I can keep going like this and find this after 9 years, but it's going to be pretty tedious, isn't it? Now, what if the question asks for 30 years? Well, you're not going to do this 30 times. It's just too time consuming. That is why we find these patterns and derive formulas. Now, let's draw this. So we have our principal here. Actually, all right, this is our principal. This is our starting amount. God, I really haven't done this well, have I? Okay, we have our starting amount. And then after 1 year, we had, well, 5,460. But what did we do to get from our starting to here? Well, we multiplied by, let's do a different color here. To get from here to here, we multiplied by 1.092, right? And, okay, so year 2, Well, we took this and we multiplied it again, actually, by 1.092. And we got 5,962.32. Sorry, I'm actually going to fix this because this is just bothering me how badly this is drawn. So our starting was 5,000. All right. Last step, we multiplied again by 1.092. We took this and multiplied it again. And after 3 years, we got 6,510.85. Now, we can keep doing this, but what pattern are we realizing here? Are we seeing anything here from all of my information on this left-hand side related to this right-hand side? Well, for each year, we're multiplying that number of year lots of 1.092. So each time we've kind of taken sort of our principle and we've multiplied it by a rate increase of this. And this is happening, I should say, each time. It's multiplying by this same number. Now, because of what we know about things like indices, and when we have the same number multiplying by itself, we can write this in a type of shorthand, right? We can have this in terms of powers. So we could say that to get to, for example, here, we multiplied our P by 1 plus the rate to the power of 3. Didn't we? Because we had our principle and we just kept multiplying by lots of this rate. And three, two, one. And we can just verify this, right? Well, we can see, I'm going to take this little formula we've come up with and I'm going to just check it. I'm going to sub in my numbers, and actually I'm just going to write n up here. I'm just going to check that what I got was correct. So it should match up with this value here. So I had 5,000. You guys can check this in your calculators as well. 1 plus our rate, 0.092 to the power of 3. Now, this is the moment of truth. You can feel free to get your calculators out and test this, but I get the exact same thing. I get 6,510.85. So it's important to note here, because we're looking at interest on interest, we're always getting this relationship happening here. And if I were to keep doing this 9 times, for example, so if I wanted to find after 9 years, well, I would take my principal and I would multiply it by 1 itself, its starting amount, plus the rate increase to the power of 9. Because this has happened 9 times. So this whole thing we established in the table, 1, 2, 3, it's going to go all the way down to 9. We're going to get 9 lots of this rate increase. on the original amount owing. And plugging this into our calculator, we get a whopping $11,040.12, roughly. So this is kind of trending like we expected, because I said to you earlier that compound interest is interest on top of interest. So each of these accumulated amounts got increased, and we, with the interest included, we did interest on top of that. So we're growing a lot quicker than we did with, say, simple interest. And from the patterns we observed, this can give us a general formula. So we can say that, what about n years? So just some amount of years, we want a general formula here. And what we got, and I actually kind of cheated because I wrote it a little bit earlier, but we had our principal amount, left it as an input because we multiplied by 1, so that goes in, as well as a rate increase. Here was 9.2%, or as a decimal, 0.092. I also could have written this as 9.2 over 100. Really just comes down to personal preference. But with decimals, it's often easier to just write them there, because when we get into harder examples, you'll see why. I won't get into it too much now. But this all was raised to whatever amount of years we were looking at. So here we looked for 9 years. So this multiplication of 1.092 by itself, it happened 9 times. And in the case of n years, we have our principal with our rate increase here and our number of years. Now this thing here is our general formula for compound interest. I'll see you guys next time.